Hi everyone. Let's start now. So in the last class, we have seen isomorphism, components, and complement of a graph. In this lecture, we will study bipartite graph and trees. Let's start. So first, let me, uh, yeah. So let's see some questions and recap. So you know what is a isomorphic, right? Correct. Isomorphic graph. So isomorphism basically means you have same graph, but their drawing or labeling is different. This is the definition of isomorphism. This is the idea. This is the intuition behind isomorphism, that you have two same graph, but their labeling, their drawing is different. For example, you can notice these two graphs are not isomorphic because here you have four vertices and here you have three vertices. So these two graphs are not isomorphic. But you can notice this graph is isomorphic to this graph because basically these are same graph. This graph, they are basically same, but their drawing is different. And tell me, what about W3K3? Are they isomorphic? W3K3. What is W3? Do you remember what is W3? W3 we get from C3. So this W3 is like this. This is W3. And this K3 is basically this. So this K3 is actually same as C3. Okay, correct? This K3 is actually same as C3. And W3 is same as K4. So I can say W3 wheel graph on four vertices. This W3 means wheel graph on four vertices. Remember, W3 is the wheel graph on four vertices. Very good, Preeti, very good. So this W3 is isomorphic to K4, and this C3 is isomorphic to K3 because this is your K3. Okay, next. So remember, at as I told you that this graph isomorphism problem, this is an NP intermediate problem, NP hard problem. In your GATE syllabus, you don't have this NP hard, NP complete, NP intermediate. This complexity classes you don't have in the GATE syllabus. So you don't have to worry about it. I just want to tell you that at this moment in this world, no one has efficient way of checking isomorphism. So, okay, so there is at this moment, there is no efficient way, to check isomorphism. If you want to check isomorphism, there is no efficient way. What you can do, you can eliminate options. This is what you can do. You can eliminate options by seeing violation of some properties. These properties are called graph invariant. Graph invariant means those graph properties which are same for isomorphic graph. Means isomorphic graph must have same, these properties must be same for isomorphic graph. Remember one thing I told you, that even if 10,000 properties are same, even if 10,000 properties are same, it does not mean, it does not prove that they are isomorphic. But in the GATE exam, what you can do, you can eliminate the options in the GATE exam. And if you have small graph, okay, if you have small graphs, then you can basically solve the question very easily. If you have a small graph, for example, in the GATE exam, if they give you this, in the GATE exam, if they give you this structure they give, and another structure they give is like this, then you can directly say that they are isomorphic. These two structures, they are isomorphic. Why these two structures are isomorphic? See, if you notice that this front is same as this. This is your front. If you notice, this is your front. This is your front. If you notice, okay, and this is your back. So basically, they are same. Very simple. So in the GATE exam, if they give you obvious things, if they give you, then there is no problem in the GATE exam. If they give you small graph, then there is no problem. For example, tell me about this. You can notice. Tell me this graph, this path graph P4. Is this is this self-complementary? This P4, is this self-complementary? Tell me. Think about it and tell me. Is this self-complementary? Is this what is P4? This is P4. A, B, C, D. This is your P4, right? This is the P4 that you have, A, B, C, D. Now, what will be P4 complement? P4 complement. What is that? So this is your path graph on 4 vertices. So your P4 complement will be like this. That okay, A will be connected to C. C, this A will be adjacent to C. This B will be adjacent to D. This A will be adjacent to D. Correct? This will be your okay. Anyway, this will be the idea. So I can say this is B and this is D. So you can notice that this is also path graph on 4 vertices. So this P4 bar is equal to P4. This is, they are isomorphic. Yes or no? So I can say P4 is isomorphic to P4 complement. Both are isomorphic. So this is this is self complementary. Yes, because the complement of P4 is also a P4. This is your P4 and the complement is also a P4. This is also path graph on 4 vertices. This is also path graph on 4 vertices. So I can say this P4 is self complementary because it is isomorphic to its own complement. Is there any self complementary graph on 6 vertices? What do you think? Is there any self complementary graph? Is there any self complementary graph on 6 vertices? The answer is no. But why? The answer is no. There is no graph on 6 vertices which is self complementary, because I told you that if your graph is self complementary, if G is self complementary, then what should happen? If G is self complementary graph, then 4 divides, I can say, then number of vertices in G, remember, number of vertices in G is multiple of 4, is I can say is 4k or 4k plus 1. Correct? Yes or no? Agree? So if G is self complementary, then number of vertices is 4k or 4k plus 1. Because you know that if G is self complementary, then you already know that 4 divides n, or 4 divides n minus 1. Either 4 will divide n or 4 divides n minus 1. So I can say either n is equal to 4k, either this n is equal to 4k, or I can say n minus 1 is equal to 4k. Correct? Yes or no? Yes or no? Is this clear? Your G, if this G is self complementary, if this graph G is self complementary, and let us assume number of vertices in G, let's just assume that number of vertices in G is n. Okay, let's assume this is the idea. Now you know what you know. Tell me what you know. You know that 4 divides n or 4 divides n minus 1. So 4 divides n, what it means? It means n is equal to 4k. Or 4 divides n minus 1, what it means? It means n minus 1 is equal to 4k. So n is equal to 4k or 4k plus 1. So from this, what I can say, from this and this, what can I say? I can say n is equal to 4k or 4k plus 1. So either n must be multiple of 4k, either n should be multiple of 4, or n should be multiple, or n should be like, when you divide n by 4, then either remainder should be 1 or remainder should be 0. Correct? Yes or no? So in self complementary graph, this is what we can say. In self complementary graph, number of vertices, if your number of vertices is n, in self complementary graph G, when you either this should be 0 or this should be 1. When you divide this number of vertices by 4, then either the remainder should be 1 or the remainder should be 0. Okay, is there any lagging? Hello? Now is it fine? Let me check. So did you miss anything? Please tell me. Did you miss anything? So your graph is self complementary. If your graph is self-complementary, then you know that 4 divides n or 4 divides n minus 1. This we know. If 4 divides n, then n is equal to 4k. If 4 divides n minus 1, then n minus 1 equal to 4k. In every case, n is equal to 4k or 4k plus 1. So I can say that if you divide the number of vertices by 4, then remainder should be 0 or 1 in a self-complementary graph. If your graph is self-complementary, then this will happen. Correct? So tell me, is there any self-complementary graph on 6 vertices? No. Why? Because what is 6 mod 4? 6 mod 4 is 2. 6 mod 4 is 2. Okay, so this is not equal to, like, 6 mod 4 is 2. So I can say no no, on 6 vertices there is no self-complementary graph. There does not exist any self-complementary graph on 6 vertices. What is the answer for this question? Is there any self-complementary graph on 2 vertices? The answer is again no. Because remember, if you have a self-complementary graph, then number of vertices should be equal to 4k or 4k plus 1. The number of vertices should be equal to 4k or 4k plus 1. So this answer is also okay. Do we have a graph, self-complementary graph on one vertex? Is there any self-complementary graph on one vertex? Yes, you can take this vertex, because what is the complement of this graph? The complement of this graph is this itself. Remember, when you find complement, then you only do the complement of edges. You don't change the vertices. This you already know, that if you have v comma e, then how to find complement? Then g dash means number of this vertex set must be same. You do the complement of edges. Okay, so this is our theorem. Our theorem is, if G is a self-complementary graph, then number of vertices, that will be either 4k or 4k plus 1. But the converse is not true. Okay, tell me, if a graph has 4k vertices, can I say this is self-complementary? My question, G has 4k vertices. G has 4k vertices. Then G is self-complementary. Is it true? Can I say if G has 4k vertices, if G has 4k vertices, then can I say G is self-complementary? The answer is clearly no. No. The answer is clearly no. You can take this example. Take this example, A, B, C, D. So here you have number of vertices is 4k. 4 multiplied by 1. This is your k. Okay. So this is the graph. Now, if you find G complement, then what that will be? That will be G, D, B, C. You can clearly see that G is not isomorphic to G complement. So this G is not self-complementary. This is not a self-complementary graph. So this is the idea. The converse is not true. Okay, let's move on. Find some isomorphic drawings of K4. So this K4, complete graph on 4 vertices. How can I draw this? So for example, this is how you can draw. You can draw like this. Remember, K4 means every vertex is adjacent to every other vertex. So you can draw like this, or you can draw like this, or you can draw like this. Or what I can do, see, or what I can do, this vertex I can pull out like this, adjacent to everything. I can make it adjacent to everything. So this is also K4. So like this, you can draw the K4, very simple. Okay, for example, you can draw the K4 like this also. You can draw the K4 like this also. This is also K4. All these are K4. All of them are K4, correct? You can draw the K4 like this also. You can draw like this, and you can draw like this. So basically, this is how you can draw K4, like this. Okay, so there are many isomorphic drawings of K4. All of them are K4. All these graphs, these are basically K4. All these graphs are K4. Okay, so quite simple. Like this you can do. Okay, let's move on. So Define the connected graph in terms of number of components. You know what is a connected graph? Connected graph means between, okay, for all a comma b, there exists a path. There exists a path. For every two vertices, there exists a path. For all a comma b, there exists a path. Another definition is number of components is one. Okay, connected graph if and only if number of components is one. If number of components is equal to one. So when your number of components is equal to one, then we will call it a connected graph. Very simple. This is the definition of connected graph. These are the two definitions. One definition is for all pair of vertices, whatever two vertices you take, there should be a path between them for all a comma b. Or I can say number of components is one. The next is some theorems. Now we will solve some questions. All these theorems, they can ask you in terms of questions. They can create questions from these theorems. Let's see the first one. Tell me one thing. For a connected graph, the complement, can I say it will definitely be connected? Like if you have a connected graph, let's assume you have a connected graph, then can I say complement will definitely be disconnected? Can I say complement will definitely be disconnected? Can I guarantee this? Can I guarantee this? Tell me. That connected graph complement will be disconnected. The answer will be no. Because for example, you can consider this graph A, B, C, D. This graph is connected and its complement that is also connected. Its complement is also connected. You can notice its complement is also connected. So this is also connected. So this is also connected. This is also connected. So I can say that a connected graph complement need not be disconnected. And can I say connected graph complement is connected? Can I say connected graph complement? Like if I give you this connected graph, for example, A, B, C, let me give you this connected graph. Then what is G complement? G complement will be disconnected. G complement will be disconnected. And this is your connected graph. So what can I say finally? I can say for a connected graph, the complement will be either connected or disconnected. Yes, correct. And what about disconnected graph? See, this is a disconnected graph. So its complement will be this. So for disconnected graph, the complement can be connected. Yes or no? For a disconnected graph, the complement will be this. For a disconnected graph, the complement can be connected. The interesting question is, can you give me a disconnected graph whose complement is disconnected? Give a disconnected graph. Can you create a disconnected graph? Please try. Can you give a disconnected graph whose complement is disconnected? Whose complement is also disconnected? Who is also disconnected? So can you try? Can you try? A single vertex graph is connected. Single vertex graph is connected or disconnected? Please tell me. Single vertex graph. This K1 means single vertex graph. This is connected because it has only one component. This is connected. This is not disconnected. This has only one component. So this is actually connected. This is not disconnected. Don't call it disconnected. This is not disconnected. This is not a disconnected graph. This is a connected graph because only one component you have, only single component you have. This is the definition of connected. And what about, this is my question. Can you give me a disconnected graph whose complement is also disconnected? Anyone want to try? Anyone has some ideas? Like, do you want to try or not? So anyway, the answer is whatever you do, it is not possible. The answer is not possible. The answer is not possible. So if you have a disconnected graph, if your graph is disconnected, then its complement will also be, then its complement will definitely be connected. If you have a disconnected graph, its complement will definitely be connected. But how to prove it? So this is what we want to prove. The complement of disconnected graph the complement of disconnected graph is necessarily connected. First of all, you tell me the first statement. Is it true? Is it true that complement of connected graph is necessarily disconnected? Complement of connected graph is necessarily disconnected. This statement is false. We have already seen this is a connected graph whose complement is not disconnected. So for a connected graph, the complement can be connected or disconnected. Now we have to prove that complement of disconnected graph is necessarily connected. This is what we have to prove. And the proof is actually very simple. Okay, so this is what we have to prove. You have to prove that if G is disconnected, then G complement is connected. This is what we have to prove. This is okay. So now let's see. Preeti is saying, can we say that a complete graph, the complement is disconnected? Yes. If you have, what is the complement of complete graph? Can anyone tell me? What is the complement of complete graph? That is the edgeless graph. That is the null graph. Correct or not? So if you have K3, complete graph on 3 vertices, then the complement will be null graph on 3 vertices. And of course, you can check that the complement of complete graph will be disconnected if and only if n is greater than or equal to 2. If you have K1, the complement of K1 will be K1. Yes or no? The complement of K1 will be K1. Now let's prove this. If G is disconnected, this is given to you. If G is disconnected, this is given. Then G bar is connected. This is what I want to prove. I want to prove that G bar is connected. And what should I do? What is your suggestion? G bar is connected. What should I do to prove that G bar is connected? The proof is like this. What you do? Let me take 2 vertices in G bar. Let me take any 2 vertices in G bar. Okay. If it is connected, then what should happen? If it is connected, then what should happen? If I take 2 vertices in G bar, if I want to prove G bar is connected, what should happen? There should be a path exist. See, you take 2 vertices, whatever 2 vertices you take. So just take 2 vertices in G bar. Now, basically we have to prove. What we have to prove? We have to prove that there is a path from A to B. This is what we have to prove. Correct? Agree? Very simple. This is what you have to prove. So you are taking 2 vertices in G bar and you have to prove that there exists a path between these two. Now for these 2 vertices, in G, what are the 2 situations? For these 2 vertices in G, what are the situations? See, there is a case 1. What is the case 1? That A, B are adjacent. In G. Yes or no? This is the possibility that they are not adjacent in G. Let's assume only these 2 cases are possible. Case 1, A, B are not adjacent in G. Correct? Either this possibility or what is another possibility? Either A, B are adjacent or A, B are not adjacent. So either A, B are adjacent or A, B are not adjacent in G. Okay, very simple. Only 2 cases are possible. So what I'm doing, this is my graph G and this is my graph G bar. Tell me, vertex set is same? Yes or no? Vertex set is same, right? For G and G bar, vertex set is always same. So you know that if G is V, E, then G bar is V, E bar. Vertex set will be same. You know that vertex set will be same. So this vertex set is going to be the same. This always will be the same. So that is the reason I'm saying that I'm taking 2 vertices and I'm saying that this is what we have to prove. We have to prove that there is a path. Now for these 2 vertices in G, what will happen? In G, what will happen? In G. So either they will be adjacent or they will not be adjacent. If they are not adjacent in G, then can I say they will be adjacent in G bar? If they are not adjacent in G, means there is no edge between them in G, then it means what? It means A, B are adjacent in G bar. Adjacent in G bar. So there is a path. So there is a path. So I can say that a comma, so there is a path between a comma b. So there is a path between a comma b. So this case is done. Yes or no? This case is over. We have done this case. Now what? Now what? Now this case is remaining. A comma g are adjacent in G. If a comma g are adjacent in G, but G is disconnected, right? You agree that G is disconnected. It is given to you that G is disconnected. And a comma b are adjacent. It means a comma b are in one component. It means they are in one component, like C1. They are in one component. Yes or no? Because they are adjacent, right? They are adjacent. So they are in one component. Agree? Yes or no? In G, they are in one component. In G. So in G, from G point of view, they are in one component. And G is disconnected. This G is disconnected. So in G, you have another component also. At least two component you have. In G, you have at least two component. So you have at least two component in G. So there is some vertex here. Tell me one thing. Can I say they are adjacent? Do we have are they adjacent? A comma Z? No, because they are different components. C1 and C2, they are different components. So they are not adjacent. They are not adjacent because this C1 and C2, they are different components. So what will happen in G bar? Now tell me what will happen in G bar. In G bar, what will happen? If they are not adjacent, then they will be adjacent in G bar, and they will be adjacent like this. Yes or no? So finally, what it means? What it means? It means there is a path between A comma B. It means there is a path between A comma B. It means there is a path between A comma B. And this is what we wanted to prove. So whatever case happens, case 1 or case 2, whatever happens, there is a path between A comma B. Yes or no? Did you understand the proof? See, okay, just understand, please understand. See, G is a disconnected graph. This is given to you. What it means, if graph is disconnected, what it means? Tell me. Disconnected graph, what it means? First, you tell me disconnected graph means what? Disconnected graph implies at least two components. You have at least two components. There are at least two components in G. Okay, you have a disconnected graph G, then it means there are at least two components in G. In G, you must have at least two components, C1 and C2. Okay, there must be at least two components, at least. There can be more. You must have at least two. Okay, next, what you have to understand. So G is disconnected. This is given to you. We have to prove that G bar is connected. So what we have to prove? G bar is connected. This is what we have to prove. In G bar, if you take two vertices, then to prove that this is connected, what we have to prove? We have to prove that there is a path between A comma B. So actually, this is what we have to prove, that there is a path between A comma B, whatever two vertices you take in G bar, because this is what we have to prove, that G bar is connected. To prove this, we have to prove that whatever two vertices you take in G bar, there should be a path. Is this clear, Devacharan? Everyone else, this is clear? This is what we have to prove. So this is what we have to prove. Okay, now tell me one thing. Two cases are possible for these two vertices because vertex set is same. G and G bar, they have same vertex set. Their vertex set is same. So what you can do, for these two vertices, you can check what will happen in G. For these two vertices, two things can happen. Either they are not adjacent or they are adjacent. Yes or no? If they are not adjacent in G, then in G bar they will be adjacent, because in G there is no edge between them. In G basically there is no edge between them. So in G bar there will be edge between them. So I can say this is your case 1. What is case 2? Case 2 is saying that A comma B are adjacent. It means they are in the same component. Yes or no, Devacharan? It means they are in the same component. So this A comma B, you can notice they are in the same component. And this graph G is disconnected. It means there is one more component, at least one more component you have. At least one more component you have. Okay, now in this component, you take this vertex Z. Now this is happening in G. Remember, This whole thing is happening in G. So what will happen in G bar? This whole thing is happening in G. Then what will happen in G bar? Tell me. In G bar, because remember, in G there is no edge. In G there is no edge between A comma Z. So in G bar there will be edge between A comma Z. And in G there is no edge between B comma Z. So in G bar there will be edge between B comma Z. So this is your path. This is your path from A to B. So we have a path from A to B. So whatever case you have, case 1 or case 2, whatever case you have, G bar will have, in G bar, for every 2 vertices we have path. So whatever 2 vertices you take in G bar, you have path. You have path. So whatever 2 vertices you take, they have path. So I can say G bar is connected. Is this clear to everyone? This proof, did you understand? This is a very simple proof. Only definitions we are using. Can you notice only definitions we are using? So if you have disconnected graph, then its complement is definitely connected. Remember, disconnected graph complement is definitely connected. But a connected, if you have a connected graph, its complement can be connected or disconnected. Its complement can be connected or its complement can be disconnected. So this is what we have. How many understood this proof? This very simple, cute proof, very cute, right? Like, I hope you are finding this very simple. Only definitions we are using, nothing else. Just using the definitions. We are using the definition of connected. We are using the definition of disconnected. We are using the definition of complement. So these things we are using. Only definitions we are using. The definition of connected, definition of disconnected, definition of complement. These 3 definitions we are using. So this is a simple proof. Okay. So prove that complement of a disconnected graph is connected. This we have done. Now let's see. This we have also done. If your graph is isomorphic to G complement, if G is isomorphic to G complement, what it means? It means it is self-complementary. Then number of vertices will be 4k or 4k plus 1. This we have already seen. Now let's see. Let's move on. Is this statement true? What do you think? Is this statement true? If a graph has exactly 2 vertices, this statement I want to ask. So let's frame this as a question. Let's frame this as a question. So tell me, is this statement true? If a graph has exactly 2 vertices of odd degree, there are exactly 2 vertices of odd degree, then they are connected by a path. Then they are connected by a path. Why this statement is true? Before this statement, you tell me, every component is a graph, right? Yes or no? Every component is also a graph. Every subgraph is also a graph. Correct? Every subgraph is also a graph. Every subgraph is also a graph. This you already know. Every component is also a graph. Correct or not? Every component is also a graph. Yes. So for example, if you take any graph G, okay, let's assume you take this graph G. Then you can notice this is also a graph, right? So you have a graph G. This is your graph. In this graph, you can notice this is also a graph. Correct or not? This is also a graph. And what about this? This is also a graph. This is also a graph. So every subgraph is also a graph. Every component is also a graph. Very simple thing. Now tell me, what do you think? If you have exactly 2 vertices, can they present in different components? Just tell me this point. If you have 2 odd degree vertices, let's assume you have exactly 2, not more than 1, not more than 2, not less than 2. Let's assume you have A comma B. Is it possible they are in different component? Is it possible that A comma B are in different component, because there are exactly two vertices. Only these are the odd degree vertices. There is no other odd degree vertex. So is it possible that A comma B are in different component? The answer is very simple. The answer is very simple. That is no. Because if they are in the different component, like A is here and B is here, then what will be the problem? What will be the problem? Now this graph has odd number of odd degree vertices. Yes or no? Now this graph has odd number of odd degree vertex. Correct or not? Now this graph has, now this graph has, now this graph has odd number of odd degree vertices. Odd number of odd degree vertices. And how many odd degree vertices a graph should have? In a graph, it is given. See, Arpan, it is given that exactly two vertices are of odd degree. Let's assume these are two vertices of odd degree, A comma B. These are the two vertices of odd degree. Exactly two. Exactly two means no more than two, not less than two. You have exactly two vertices of odd degree. All other vertices have even degree. Only two vertices are odd degree. This is given to you in the question. If a graph has exactly two vertices of odd degree, exactly two, not more than two, not more than two, not less than two. So these two vertices are of odd degree, A comma B. Is it possible they can be in different components? Yuvraj, tell me. Is it possible they can be in different components? Is it possible? If they are in the different components, think about it. If they are in the different components, then what will happen? Then this graph has odd number of odd degree vertices. Then this graph has odd number of odd degree vertices, and that cannot happen. We know that every graph has even number of odd degree vertices. But if in this graph now how many? In this graph now you have one odd degree vertex. One odd degree vertex you have. So odd number of odd degree vertices you have. So that is the contradiction. Basically, it is the contradiction. Yes, this is not possible. So they should be in the same component. So A comma B should belong to same component. And what this means? So they should belong to same component. And what this means? This means that there is a path between them. It means there is a path between them. Very simple. Okay, clear? But it does not mean they will be adjacent. Does it mean they will be adjacent? Does it mean they will be adjacent? No, they can be like this. You can notice, but they will be in the same, they will be in the same component. In this graph, you have exactly two vertices. You can notice in this graph, you have exactly two vertices of odd degree. In this graph, exactly two vertices of odd degree. This vertex, this vertex. So you have exactly two vertices of odd degree. They are in the same component, but they need not be adjacent. Is this clear, Mayuk? Okay. So this is the idea. If your graph has exactly two vertices of odd degree, then they will definitely be connected by a path. This same question people can ask you like this. Yes, Manideep, every graph has even number of odd degree vertices. We have already seen. The proof we have seen. The questions we have seen. 3 gate questions we have seen. I told you. In the gate exam, 3 questions have come. And in the last lecture, we have taken those 3 questions. Back to back, 3 questions have come in the gate exam. All the 3 questions are on the same point. That in every graph, whatever graph you take, in every graph, we have even number of odd degree vertex. Remember, every component is also a graph. Every subgraph is also a graph. Every component is also a graph. So if you notice every component is a graph. Just notice every component. Every component is a graph. Okay, so in every component, what should happen? You should have even number of even number of odd degree vertices. You cannot have odd number of odd degree vertices. The same question they can ask you like this. Show that in any simple graph, there is a path from any vertex of odd degree to some other vertex of odd degree. Basically, what this is saying, what this question is saying, this question is saying that whatever simple graph you take, then definitely there should be a path from a odd degree vertex to some other odd degree vertex. For example, it's like in any simple graph, if you are odd degree vertex, for example, if A is odd degree vertex, if you are odd degree vertex, then definitely you will have a path to some other odd degree vertex. Definitely you will have a path to some other odd degree vertex. This is what this question is saying. Is this clear? In any simple graph, if you are the odd degree vertex, then definitely you have path to some other odd degree vertex, because it is not possible that you are the only one. Yes or no? It is not possible that you are the only one, only odd degree vertex in a component. It is not possible. Agree? Correct? It is not possible that you are the only odd degree vertex in a component. So definitely you must have a path to some other odd degree vertex. Tell me, the same question they can ask you in two different ways. The same question is they can ask. Okay, now this is your TIFR 2018 question. What will be the answer? TIFR 2018. In an undirected graph, you have an undirected graph G with n vertices. Vertex 1 has degree 1, vertex 2 has degree, each vertex 2 to n minus 1 has degree 10. Degree of vertex n is unknown. Total n vertices you have. Which of the following statement must be true? Which of the following statement must be true? So the question is saying that there are total n vertices. There are total n vertices. There are total n vertices. This vertex, this vertex, this vertex, this vertex, this vertex, and this vertex. This vertex has degree 1. So what is the degree? This vertex has degree 1. This has degree 10. This has degree 10. This has degree 10. This has degree 10. What should be the degree of this? Anyone want to tell me? Anyone want to tell me what should be the degree of this? Odd. It should be the degree odd. You must have degree odd. Okay, so the idea is very simple. See, all of them are even. All of them are even. And this is the odd degree vertex. So definitely from this vertex, definitely there must be a path. Definitely this n must be odd. First of all, definitely this n must be odd, and there must be a path. So this is odd. Definitely this should also be odd, and there should be a path. There should be a path. Can you notice? Very simple, right? If you notice, this same question they can ask you in 3 different ways. See, this same statement they are asking, they can ask like this, they can ask like this, or they can ask like this. And this is your TIFR 2018 question. So finally, you can notice that this is odd degree vertex, all other are even degree vertex. Remember, it cannot be even, because in a graph, you should have even number of odd degree vertices. So this vertex n, this should have odd degree. This definitely should have odd degree. And I told you that if you are odd degree vertex, for any odd degree vertex, what we can say, if you are odd degree vertex, then there is a path from you to some other odd degree vertex. Correct? So this is the idea. So finally, I can say that there is a path from 1 to n. This option is correct. There is a path from 1 to n. Vertex n has degree 1. It is not mandatory. Vertex n has degree 1. This is not mandatory. But vertex n should have degree odd. N should have odd degree. Okay. So very simply, they can ask you this question in this, like this, they can ask. So remember this point always. always understand a statement. By hearting will not help you. Let me tell you, for example, if you by heart this statement, then I can guarantee that you will not be able to solve this question. If you by heart this statement, if you just by heart, like like तुमने रट्टा मार लिया इस statement का, you have by hearted this statement. Now I can guarantee that you will not be able to solve this question. Because why? Can anyone tell me why? Because you will not even feel this question. You will not even get the idea to apply this statement to this question. This idea you will not get if you don't understand this statement. What this statement is saying? This statement is saying that if you are odd degree vertex, then definitely you have path to some other odd degree vertex. Definitely this will happen. If you are odd degree vertex, then you have path to some other odd degree vertex. Or I can say, if there are two odd degree vertices, exactly two odd degree vertex you have, then they are in the same component. They must be in the same component. Okay, so this is the idea. Have you heard about this dialogue of Three Idiot? There is a dialogue in Three Idiot. This हमने तो सुना था, उसने apply किया. This dialogue is there. The almost first scene. You know, there is a dialogue in Three Idiot movie. There is a dialogue like this. कि हमने पढ़ा था, उसने apply किया. This dialogue is there. And this is actually very interesting dialogue. See, seriously, this is very interesting dialogue. This is very important dialogue for GATE exam also. Many people, they do this. Let me tell you. Okay, how many people do this? Let me tell you, almost 15, almost 10 to almost 10,000 people. Almost 10,000 people, they cover the syllabus. Almost there are 10,000 people, they cover the syllabus. They cover the syllabus. You remember? They cover the syllabus. See, these are the 10,000 people who cover syllabus. Who cover syllabus. And these are the people, and these are the almost 1,000 people. And these are almost 1,000 people who understand the syllabus. Who understand the concepts, I can say. They cover, these people cover the concepts, and these people understand the concepts. So this is the difference. This is the difference between toppers and all. Okay, so please be in this category. Whatever you study, you study by understanding. If you are study by understanding, then okay, basically this is very important. Whatever you study, like if I tell you some definition, if I tell you some idea, then you have to apply that to the question. Okay, so this is the idea. Anyway, now let's move on. So tell me the answer for this. Suppose you have a simple graph G with n vertices. Remember, simple graph is given to you on n vertices. What is the maximum number of edges if it is undirected graph? You have a simple undirected graph. Then what is the maximum number of edges for simple undirected graph? That will be NC2. You already know. Maximum number of edges for simple undirected graph. And for simple directed graph, what will be the answer? For the simple directed graph, what will be the answer? For simple directed graph, the answer will be n into n minus 1. The answer will be n into n minus 1 because this is directed graph. So you have ordered pairs. This is a directed graph. So you can have this, a simple directed graph. You have a simple directed graph. So if you have simple directed graph, this is allowed. So if you want to find maximum number of edges, then what that will be? That will be ordered pair. So every edge will be an ordered pair. Every edge will be ordered pair. So for this, we have how many choices? For this, you have n choices, and here you have n minus 1 choices. Because we are talking about simple graph. So you cannot have self loop. Yes or no? You cannot have self loop. So we are talking about simple directed graph. So the answer will be n into n minus 1, because we are talking about a directed graph. In the directed graph, every edge is a directed pair. So for the first element, you have n choices. There are n choices. Now for the second element, you have n minus 1 choices. We have ordered pair. This is ordered. Order matters. Okay. So the answer will be n into n minus 1. Like this. Tell me the answer for this question. Are they isomorphic? These two. These two, are they isomorphic? On your screen. Yes, this is also path graph. This is also path graph. What you can do, you can take this and you can shift it here. This V3 you can shift here. Can anyone give me a bijection between this and this? Can anyone give me a bijection which will preserve the edges? Can anyone give me a bijection which will preserve the edges? Yes, this bijection you can give. These two, you basically, this V3 you can untwist. This V3 can, so U1 will be same as V3. U1 will, okay, so whatever, like you can do this. Okay, so you can give a bijection. And these two we have already seen. These two we have already seen that these are isomorphic. Correct? So just give me a second, okay? Give me a second. You solve this question. So after this question, what you do? You solve this one. So try this. Are these two isomorphic? Are these two isomorphic? Okay, so you can notice these two graphs are not isomorphic, because you can just see the degree sequence. The degree sequence is different. And what about these two graphs? These two graphs are actually isomorphic. These two are actually isomorphic, because see, okay, let me tell you one interesting thing. How to check that these two graphs are isomorphic? How to check? You can notice one thing. Just notice this graph. If you notice this graph, it will tell you how to check. What this graph is, this is a complete graph, and this vertex is, see, this is a complete graph. You have a complete graph. Tell me, in a complete graph, does it matter which, like, all the vertices are symmetric, right? Yes or no? This is a complete graph. In a complete graph, all the vertices are symmetric. So basically you have this, and this you can put to any. This will be isomorphic to, like, if I give you a complete graph, and if I do this, then that will be same, right? Yes or no? These will be same, because in a complete graph, the vertices are isomorphic. So the same thing is happening here. What is happening? That you have this like this. So you have a complete graph. You have a complete graph like this. Like this, you have a complete graph. And then this vertex you have, and this vertex you are adding like this. This vertex you are adding like this. This is what is happening here. Yes or no? This vertex V2 you are adding to this complete graph. This is your complete graph. This is your complete graph. And this vertex you are adding to two of the vertices. This is what is happening. So actually in the GATE exam also, they will give you question, this type of some nice argument you can apply. This type of, yes or no? Like you have a complete graph. This same graph, they can give you like this. You have a complete graph. For example, this is a complete graph. And then what you can do? Then you can do like this. They are also same. Yes or no? Agree? So like this, these are isomorphic graphs, all of them, because you have a complete graph and you are adding a vertex to two of the vertices. What about this? Are these isomorphic? You can notice here we have a 3-length cycle. Here we don't have a 3-length cycle. There is a 3-length cycle. Here there is no 3-length cycle. So I can say they are not isomorphic. Let's see the next topic, that is bipartite graph. What is this? And this is very important, bipartite. The name itself is telling you bipartite means you can partition into two categories. Bipartite means, this bipartite simply means that if you can partition into two, bipartite means two partition. Bi means two and partite means partition. This partite simply means partition, two partition. It means if I give you a graph, for example, let me take example. Let's consider this graph A, B, C, D. Okay, this graph I can partition. This graph, what I can do, the vertex set of this graph, I can partition into two categories. I can partition these two vertices, I can put in one part, these two vertices I can put in another part. And what I'm doing, you can notice one thing, one interesting thing you can notice. There is no edge in this part, yes or no? In this part, there is no edge. In this part, there is no edge. In this part, there is no edge. All the edges are between the parts. All the edges, if you notice, all the edges, they are between the parts. All the edges are between the parts. So this is the idea. Bipartite graph means you can create two partition such that you can create two partition x comma y. These are your two partition x comma y. You can create two partition x comma y such that there should be no edge here. There should be no edge here. There should be no edge here. All the edges, if you have edges, then they should be here. All the edges must be between the parts. There should be no edge here. There should be no edge here. You can partition the vertex set. The vertex set you can partition into two parts. For example, here you can notice in this example, just notice in this example, what is your vertex set? That is ABCD. This vertex set you can partition into two parts, A comma D and B comma C. And you can notice one thing, these two parts you got, and there is no edge in this part. There is no edge in this part. So I can say that because this graph you can partition, into two parts, such that there is no edge here, there is no edge here. All the edges that you have, those edges must be between the parts. Then this graph will be bipartite. So remember, this graph is your bipartite graph because you can represent this using two partitions. Is this clear to everyone? Please tell me. So understand, see, what I want to say, what is a bipartite graph? If you have a graph G, you have a graph G in which you have vertices, in which you have edges, is bipartite if and only if bipartite if and only if this graph is bipartite if and only if there exist two part of V, there exists a partition. I can say there exists a bipartition. There exists a bipartition of V. There exists a bipartition x comma y of V. Okay. What should happen? These things should happen. These two parts, they should be disjoint because this is like a partition. Have you seen partition in set theory? Partition of a set. This is a set, right? This is a set. So this is subset of vertex set. So I can say that you are creating a partition of V. You are creating a partition of this set. So what should happen? The intersection should be phi. Means these two must be disjoint. Also, what should happen? Between any two vertices of X, there should be no edge. If A comma B, I can say that for all A comma B, I can say for all A comma B belonging to X, what should happen? A comma B should not belong to edge of G. Okay, and similarly for any vertex, if you take any two vertices A comma B in Y, then what should happen? There should be no edge between them. Means there should be no edge in this part, there should be no edge in this part. Okay, so these are the two conditions. And let me tell you third condition also. that they can be empty also. X comma y can be empty. X union y must be V. X union y must be V. And the fourth condition is that they can be empty also. X comma y can be empty. Can be empty. All other conditions are same as partition of a set. Only this condition is not same as partition of a set. Because remember, when we do the partition of a set, a part cannot be empty. Yes or no? Yes or no? Do you remember? Partition of a set. When you do partition of a set, then a part cannot be empty. But this is the only change. Only this is the change. So you have vertex set. Idea is very simple. You have this vertex set, and this vertex set you can part in two categories, X comma Y, such that all there should be no edge here. There should be no edge here. There should be no edge here. And remember, X union Y should be equal to V, and they should be disjoint. They should be disjoint, and there should be no edge here. There should be no edge here. All the edges must be here like this. All the edges must be between the partition. Okay, whatever edge you have, they should be between the two parts, this part and this part. This is the definition of bipartite graph. Let's see with example, this concept will be clear. Okay, can anyone give me a partition of this set A, B, C, D, E? Is this bipartite? This graph is bipartite. Can I say this is bipartite? Can you create a partition of this? Is this graph bipartite? Like, can you create partition? Can you create like this, such that there is no edge here, there is no edge here? Can you create like this? Let's see. This is your graph. Can you create two parts? Let's see. See, if I put A, then tell me where to put B. If I put A here, where to put B? Tell me. B I cannot put here, because remember, if I put B here, then they will be adjacent. I cannot put B here, because remember, within a part there should be no edge. Within a part you should not have edge. Within a part you should not have adjacent people. In this part you cannot have adjacent people. In this part you cannot have adjacent people. Okay, so if I put A here, then automatically B should be here. Automatically C should be here. And what about D? What about D? Can I put D here? Tell me. Can I put D here? No. If I put D here, then these will be adjacent. If I put D here, there will be edge. There will be edge. So I cannot put D here. Can I put D here? Tell me. Can I put D here? Yes, I can put. Because you can notice there is no edge between these two. There is no edge. And where to put E? Can I put E here? I cannot put, because they are adjacent. So I have to put E here. Now you can notice that. Again, I cannot put E also. This E, where to put E? Just tell me. See, where to put E? This is interesting. Where to put E? I cannot put E. I cannot put E here. I cannot put E here. I cannot put E. So this is not bipartite. So the answer is no, because you cannot create a partition. Yes or no? See, step by step I have told you. What I did, I started with A. I started with A. If I put A here, then automatically B, C should be here. And automatically D should be here. But now where to put E? You cannot put E. So that is the reason this is not bipartite. Is this clear? This graph is not bipartite because you cannot create bipartition. This bipartition you cannot create. Is this clear? The definition of bipartite. So remember, G, V, E is bipartite. When it is possible, is bipartite if and only if you can create like this. This X, Y you can create from V. From V, you can create two parts. From V, you can create two parts, X, Y. These union must be equal to V. All the vertices must be covered. Also, intersection must be phi. They must be disjoint. These two parts, they must be disjoint. And also here, all the vertices must be non-adjacent. Here, the vertices must be non-adjacent. And here also, the vertices must be non-adjacent. Means there should be no edge here. There should be no edge here. All the edges all the edges, whatever edge you have, that edge should be like this. If you have some edge, that should be between these two. This is the idea. Is this clear? So for example, let me ask you this question. Is this bipartite? Is this graph bipartite? Tell me. This graph is bipartite? Is this graph bipartite? A, B, C. So what you will do, let's try to create. Can you create two partition? Let's see. Can you create two partition? See, if I put A here, let's assume if I put A here, now automatically where should be B? Remember, automatically B should be here, automatically C should be here. But now there is a problem. Now there is a problem. They are adjacent. Now there is a problem. They are adjacent. So this is not bipartite. So this graph is also not bipartite. So this is the idea. Okay, is it clear? So whatever graph I give, for example, if I give this graph A, B, C, D, E, F. Okay, if I have this graph, is it bipartite? Is this graph bipartite? Randomly, I am giving you some graph. So is this bipartite? So can you create two parts? Like, can you create two parts such that there is no edge here, there is no edge here. If you have some edge, if you have some edge, then that should be here. So can you create, for example, if I put A here, then where should B, C go? If I put A here, the B automatically will go here, C will automatically go here. There is no problem right now. At this moment, there is no problem because B, C are not adjacent. Okay, if B is here, then automatically D should be here. If B is here, then automatically D should be here. Now there is no problem. At this moment, there is no problem. If D is here, then E should be here. If C is here, then F should be here. So this is correct. This is correct. You can notice. This is absolutely correct. So I can say D, E, and what you have. So for example, C, F you have, and C, D you have. So this is like this is the idea. So you have a so I can say yes, this is bipartite. Is this clear? Bipartite graph. Which graph is bipartite? Which graph is not bipartite? Is it clear? Start with one vertex. Always start with one vertex and just find out the bipartition. So this is the definition of bipartite graph. Tell me which graph is bipartite. My questions, some questions I'm asking you. Pn is bipartite. For which value of n? Then what is the value of n? If Pn is bipartite, then for which value of n Pn is bipartite? This Pn, path graph. For all the values, tell me, is this graph bipartite? My question, is this graph like A, B, C? Is this graph bipartite? Tell me. Is this graph bipartite? Tell me. Is this graph bipartite? Yes, this is bipartite because you can create two parts. You can create two parts. There exist two parts. So you can create two parts. And you can notice that there is no edge in any part. There is no edge in this part. There is no edge in this part. Actually, there is no edge. So there is no problem. So this is a bipartite graph. Another question. This graph, K1, this is your K1. Is this bipartite? Is this graph bipartite? This single vertex graph, is this bipartite? The answer is yes, because you can create two parts. Like this you can create. I told you that a part can be empty. I told you a part can be empty. Okay, a part can be empty. So this is a bipartite. So this single vertex graph is also bipartite. This Pn, is this bipartite? Like P1, you can notice P1 is bipartite. P2 is automatically bipartite. P3 is also bipartite. This P3 is also bipartite because what you can do, you can put B here, A, C here. Actually, the answer will be what? The answer will be for all values of n. Whatever value of n you take, Pn is always bipartite. You can take alternative. For example, if you take P4, just assume you take P4, A, B, C, D. Then what you can do? Very simple. What you can do? You can put A here. You can put A here. then this B will go here, then this B will go here, then this C will go here, then this D will go here. So alternative you can take. So this A, B, and B, C, and C, D, like this. So Pn is bipartite, there is no problem. What about Cn? What about Cn? Cn is bipartite. Then what is N? Cn is bipartite, then what is N? If Cn is bipartite. So you can notice that C3, C5, these are not bipartite. These are not bipartite. And C4, C6, these are actually bipartite. These are bipartite. So what should be N? So the answer is actually very simple. N should be even. N should be even. Okay. Because we have already seen that C5 is C5, C3, these are not bipartite. And we have already seen that C4, C6, these are bipartite. So Cn is bipartite if and only if N is even. And what about Kn? Kn is bipartite. Then what can you say? Kn is bipartite. Then what can you say about N? If your Kn, remember in a Kn, every two vertices are adjacent. Every two vertices are adjacent. So you know that K3 is same as C3. This is your K3. This is your K4. Are they bipartite? Are they bipartite? These are. Are they bipartite? These are not bipartite. Because in complete graph, all the vertices are adjacent to each other. So for example, if you have this K4, just think about it. If you have this K4, now in this K4, this is not bipartite. Why this is not bipartite? Just think about it. If you create a part and you put A here, now because A is adjacent to everyone, so everyone should go. Because A is adjacent to everyone, A is adjacent to everyone, so everyone should go here. Now there is a problem. These are adjacent. Now there is a problem. These are actually adjacent. So what should be the value of N? The value of N should be 1 or 2. Only for these values, Kn is bipartite. So this is the idea. Okay, this is the concept of bipartite graph. This is bipartite. This is not bipartite. Cn is cyclic graph. We did not see any circuit graph. There is no graph as circuit graph, cyclic graph. Okay, so this is the idea. The idea is clear to everyone, the definition of bipartite graph. And this is very important theorem. And the proof of this theorem is not easy. So the proof we will not see because this is and this is extremely important actually. This theorem is, I can say this is extremely important theorem. This theorem is extremely important because, and the proof, let me tell you, the idea I will give you the idea of the proof, but the proof is not easy. The proof is complicated. And the most concise proof, let me tell you, in IIT, like in IISc, the proof of this theorem, they taught in 25 minutes. If a professor is teaching you a proof in 25 minutes, then you can think how much time I will take. Okay, are you getting my point? A professor is teaching 25 minutes. A professor is teaching the proof. I will take 2 days, 2 days, 3 days. Someone will say repeat. Okay, once I complete the proof in 2 or 3 hours, then someone will say, please sir, repeat once more. Okay, so anyway, we will not see that. So this theorem is very important. And the idea of the proof, let me just tell you. The idea is like this. A graph is bipartite if and only if. This is if and only if theorem. Remember, this is if and only if theorem. If and only if it doesn't have odd cycle. It doesn't have odd cycle. Okay, so this is the idea. The idea is actually like this. See what will happen in a bipartite graph. In a bipartite graph, can you create odd cycle? Just tell me, in a bipartite graph, can you create odd cycle? Let's try to create odd cycle. In a bipartite graph, there you cannot create odd cycle. Can you create odd cycle? Let's try. Let's try. For example, let me create odd cycle. So to create odd cycle, what I can do like this. Can I create a cycle of length 3? Can I create a cycle of length 3? No, because I have a bipartite graph. Because I have a bipartite graph, I cannot create a cycle of length 3. Let me create a cycle of length 5. Can I create a cycle of length 5? Can I create cycle of length 5? No, I cannot create cycle of length 5. So in a bipartite graph, you cannot create cycle of odd cycle. In a bipartite graph, you cannot create odd cycle. So if your graph is bipartite, you cannot create odd cycle. If your graph is bipartite, then there is no odd cycle. There is no odd cycle. And if there is no odd cycle, then it is bipartite. So it is if and only if theorem. This is two-way. Is this clear? So bipartite graph, there is no odd cycle. And if there is no odd cycle, so this statement, the same statement I can say like this also. Bipartite graph, it means all cycles are even. It means all cycles are even length. It means all cycles are even length. There is no odd cycle. No odd cycle means all cycles are even length. All cycles are of even length. And if all cycles are of even length, then it will be bipartite. And this is very important. From this theorem, can you try these questions? Can you try from this theorem? Which of them are bipartite? Do we have an odd cycle? So this is bipartite. There is no odd cycle. So this is bipartite. Do we have odd cycle? Do we have odd cycle here? See, this is not bipartite. This is bipartite because there is no odd cycle. Do we have odd cycle here? 1, okay, 2, 3. Okay, so there is no odd cycle. This is also bipartite. There is no odd length cycle. And what about this? Do we have an odd length cycle? Do we have odd length cycle here? Yes, there is odd length cycle here. We have odd length cycle here. Yeah, there is a triangle also. Yes, yes, yes. There is a triangle also. This triangle we have. There is a cycle of length 3. So this is not bipartite. Actually, this same question you can solve by this method. Let's solve this same question by another method, the definition method. Can you give a part? Can you give a bipartite? Very simple. A, B, D, E. This is your, so this is your bipartition. And can you give me a bipartition for this? A, B, C, D, E. Can you give me a bipartition for this? Give me a bipartition for this. So if I put A here, then automatically E will go here and C, automatically E will go here, B will go here, C will go here. And you can notice E, B, C, they are not adjacent. E, B, C, they are not adjacent. So this D should go here. There is no problem. Okay, so everything is fine. So this is the idea. A, B, this. So this is the idea. And D is adjacent to other three. So this is the idea. Now, for this graph, you can notice that in this graph, we have a triangle. These three vertices you cannot put because you have a triangle. So there is a 3-length cycle. There is a 3-length cycle. Because you have a 3-length cycle, so I can say that, so I can say this is not bipartite. Because remember, if you have odd cycle, then not bipartite. If there is some odd cycle, then it is not bipartite. What about these two graphs? Are these two graphs bipartite? What about these two? Like here, you can clearly see a cycle of length 3. Here you can clearly see a cycle of length 3. The cycle of length 3 you can see. So because you have odd cycles, so not bipartite. Okay, this is not bipartite. What about this graph? Do we have an odd cycle in this graph? Actually, in this graph, if you find odd cycle, it will be complicated. Yes or no? So what is the best method for this graph? For this graph, what will be the best method? If you find odd cycle, it will be very complicated. So the best method is like this. If I put A here, then automatically which vertices should go here? If I put A here, then this vertex should go here. 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 Because, okay, 4 vertices. So if I put A here, then these vertices should go here. Is there any problem? Are they adjacent? Any of them are adjacent? Like for example, this G is not adjacent to any of them. C is A, B, D. So C is also no problem. F, A, B, D, no problem. E, A, D, B, A, D, B, no problem. So there is no problem actually. These are non-adjacent. There is no problem. They are not adjacent. There is no problem. Now tell me, if G is here, then automatically where D will go? If G is here, then automatically where D will go? D will go here, and there is no problem. Always check the problem. Always check the problem. There is no problem. So you can put D here because A comma D are not adjacent. This A comma D, they are not adjacent. Okay. Which vertex is remaining? 3, total 7. One vertex is remaining. Which vertex? B is remaining. So if C is here, then B should be here. And you can notice there is no problem. So yes, this is the partition. For this graph G, this partition will work. So this graph G is actually bipartite. Okay. This is actually bipartite. So remember, for this question, the best method is actually this. This is the actual best method for this question. Okay, and let's see this one. Tell me one thing, very interesting. If you have a bipartite graph, like, okay, this is your X, this is your Y, can I say summation, degree summation of X? Can I say degree summation of X? Can I say degree summation of X is equal to degree summation of Y? Is it correct? Can I say degree summation of X is equal to degree summation of Y? See, very simple. Because of every age, what will happen? Because of every age, what will happen? Because of every age, the degree of this will go by +1 and degree of this also will go +1. Because of every age, whatever age you put, degree of this will go +1, degree of this will go +1. Whatever age you put, degree of this will go +1, degree of this will go +1. So because of every age, degree of X will increase by +1 and degree of Y, total degree of Y will increase by +1. So the total degree will be same, yes or no? Because whatever age you put, if you put this age, for example, if I put this age, let me put this age, then degree of this, the total degree will increase +1 and the total degree here also will increase +1. So very simple idea. So I can say if your graph is bipartite, then the total degree of both the part will be same. So total degree of X, I can say. So total degree of X, part X will be equal to total degree of part Y. Because whatever age you put, that is your choice. If you put any age, then the total degree of this part will increase by +1. The total degree of this part will increase by +1. So every age will give +1 to him, +1 to him. Okay, yes or no? Every age will give +1 to him, +1 to him, every age. So I can say their total degree will be same. Next, and this is another question. K regular bipartite. If a bipartite graph is K regular, then what you can say? If a bipartite graph is K regular, then what you can say? Like you have K regular bipartite graph. Then what you can say, tell me? So let's assume these are your parts. This is your part A, this is your part B. We already know that total degree of A, if you notice, total degree of A will be equal to total degree of B. This will be equal to total degree of B. But this is K regular. This is K regular. So every vertex has degree K. So what is total degree of this part? What is total degree of this part? The total degree of this part will be K into number of vertices here. Total degree of this part will be K into number of vertices here, because every vertex has degree K. Every vertex has degree K. Every vertex has degree K. So I can say total degree of part A, that will be K into number of vertices in part A. Total degree of part B, that will be K into number of vertices in part B. They should be same. So what it means? If I put them same, then it means their cardinality must be same. These two parts, they have same cardinality. Yes or no? So very simple. This type of question they can ask, like bipartite K regular. You have a K regular bipartite graph. So because it is bipartite, so remember, because it is bipartite, so total degree of A will be equal to total degree of B. And because it is K regular, so every vertex has degree K. Is this proof clear to everyone? K regular bipartite graph. Very simple proof. Next, what about this statement? Every subgraph of a bipartite graph is bipartite. Can I say this? Every subgraph of bipartite graph is bipartite. Can I say this? Every subgraph of bipartite graph is bipartite. What do we do in subgraph? Just tell me. If I give you a bipartite graph, like if I give you a bipartite graph, then actually what we do in a subgraph? If you create a subgraph, then what you do? To create subgraph, what you do? You delete some vertices and edges. You delete some vertices and edges. If you delete some vertices, you delete some edges, will we get a bipartite? See, you already have bipartite. This is already bipartite graph. Now, if I delete some vertices, some edges, will I again get a bipartition? Yes, no problem. For example, let's assume this type of graph you have. Let's assume you have this type of graph. Okay, let's assume you have this type of graph. Okay, this is your graph. Now, if I delete some vertices, let me delete, for example, let me delete B comma F. Let me delete B comma F. Okay, let me delete this B comma F. And let me delete this edge. For example, let me delete this edge AD. So if I delete some vertices, some edges, then again what I will get? If I delete some vertices, some edges, then again what I will get? I will get a bipartition. I just think about it. If you don't have edge here, then after deletion also you will not get edge here. Yes or no? Because we are deleting, we are not adding. Just think about it. If you don't have any edge here, then after deletion of vertex, after deletion of edge also, there is no edge here. If I don't have edge here, then after deletion also I will not have edge here. So very simple. So if you have a bipartite graph, then its subgraph is also bipartite. Very simple. Every subgraph of bipartite graph is itself bipartite. This same question, can I say this same question? Like, can I say for, tell me, the same question if I ask you for complete graph. Every subgraph of complete graph is complete. Will this statement be true? If I ask you, every graph of complete graph, every subgraph of complete graph is complete, this statement will be false. Clearly, this statement will be false. Okay, this statement we have already seen in the last class. This statement will be false. Tell me, every subgraph of cycle graph, every subgraph of cycle graph will be cycle graph. Is this statement true? Every subgraph of cycle graph is cycle graph. This statement is also false. But every subgraph of bipartite will be bipartite. Okay. Now this same question I can ask you for edgeless. Tell me, every subgraph of edgeless graph is edgeless. Yes, this statement is true. Every subgraph of edgeless will be edgeless. So very simple. Okay, is this clear? All these variations. Every graph of every subgraph of bipartite is bipartite. The proof is very simple, because if you do not have any edge here, then after deletion also you cannot get edge here. If you don't have any edge here, then after deletion also you cannot get edge here. Okay, this topic we will study tomorrow. I think that is enough for today. We have seen what is bipartite graph. Okay, so this complete bipartite graph we will actually this is a small topic, so let me just quickly complete it. What is a complete bipartite graph? The name itself is telling you complete and bipartite. What this means? Complete and bipartite. What this means? You have complete also, you have bipartite also. What do you think it means? You have complete also, you have bipartite also. These two things you have. CBG. Okay, CBG. So first of all, this should be a bipartite. It means you have like this. Okay, it means you have like this, CDE. Now it should be complete. Means all the possible edges must be there. Yes or no? Complete means all the possible edges must be there. must be there. All the possible edges must be there. This type of graph is called complete bipartite graph. This we write it like this. There are two vertices here, three vertices here. So we write it K23. This is your complete bipartite graph. Remember, this would be bipartite and every vertex of this part should be adjacent to every vertex of this part. Is this clear? What is a complete bipartite graph? This is KMN. KMN means this is a complete bipartite graph. This is your complete bipartite. This is a complete bipartite graph. It means one part has M vertex. In this part, you have M vertices. And in this part, you have N vertices. One part have M vertices. Another part have N vertices. So for example, if you have M vertices here and you have N vertices here, then because this is complete, so every vertex here is adjacent to every vertex here. Okay, and similarly, every vertex here will be adjacent to every vertex here. And similarly, every vertex, every vertex here will be adjacent. So this is the idea. Means every vertex in this part will be adjacent to every vertex in this part. I can say that for all A belonging to X, for all B belonging to Y, what can I say? For all A belonging to X, for all B belonging to Y, I can say that AB is age. Okay, AB is age. Very simple. This is the definition of complete bipartite graph. For example, this is K23. Like you have two vertices here, three vertices here. So this is K23. Every vertex of this part is adjacent to every vertex of this part. This is K33. This is K33. Every vertex of this part is adjacent to every vertex of this part. This is K35. Three vertices, five vertices. This is K35. This is K26. This is the K26. So this is the definition of complete bipartite graph. What do you think this K1, 4, what it looks like K1, 3, K1, 4, what they look like? This K1, 3. This K1, 3 means, remember, this is complete. This is the symbol for complete bipartite graph, KMN. So it means you have one vertex here and you have three vertices here. So this will be your K13. This K13 you can actually write like this: 1A, B, C. Like this you can write. One is adjacent to everyone. And this K14, you can think like this: A, B, C, D. So this is adjacent to everyone because this is complete bipartite graph. So you can think like this: this is your A, this is your B, this is your C, this is your D. This graph is actually called a star graph. Let me tell you. This is called a star graph. This is not a star garage. Do you remember star garage? Please tell me, do you remember star garage? I hope. There is something called star garage. Hera Fairy yaar. Anyone who has not watched Hera Fairy can go out of this class. I don't want to see you here. Okay. That is Hera Fairy, Star Garage, Babu Rao, Raju. Okay, so anyway, what is this star graph? A star graph means this type of graph is called star graph. This graph is called star graph. That is your like Shaktiman's chakkar. It looks like Shaktiman's, uniform. There is a on the uniform of Shaktiman there is a chakra. So something like that. So this is your star graph. Basically, the definition of star graph is like this. Can you notice what is this graph? Like, can you notice what is this graph? This graph is actually 1, 2, 3, 4, 5, 6, 7, 8. This graph is actually K1, 8. This is actually K1, 8. Yes or no? So this star graph is basically K1, N. This graph is called a star graph. This is the definition of star graph. Remember this K1, N. This graph is star graph. For example, this is your K18. This is your K14. This graph is your K14. Okay, so very simple. So this is the concept of star. Tell me how many edges you have in this complete graph, in this complete bipartite graph. let's do the complete analysis of complete bipartite graph. Let's assume m is greater than equal to 1, n is greater than equal to 1. Then tell me, first you tell me what is the number of vertices. This is your complete bipartite graph. You know this is the complete bipartite graph. So this is complete also, bipartite also. So number of vertices, that will be m plus n. What is the number of edges? Number of edges. Every vertex in this part is adjacent to every vertex in this part, so that will be m into n. Okay, what is the what is the degree sequence? What is the degree sequence? The degree sequence will be like this. See, every vertex here will have degree n. So how many vertices will have degree n? Tell me, how many vertices will have degree n? M vertices will have degree n. And how many vertices will have degree m? Total n times. Okay, so this is the degree sequence. Next, what is the maximum degree? What is the maximum degree? Tell me the maximum degree. That is max of m comma n, right? That is max of m comma n. That will be your maximum degree. What is the minimum degree? That will be of min of m comma n. Correct or not? Because remember, every vertex in this part will be adjacent to every vertex in this part. So the maximum degree will be maximum of m comma n. The minimum degree will be minimum of m comma n. And what will be diameter? What will be diameter? Diameter will be 1 for K11. For K11, the diameter will be 1 for K11. And for all other, if you have for all other, where m is greater than equal to 1 and n is greater than equal to 1, but m equal to, but they are like, but this is not m equal to, but basically not K11, but not K11. Yes or no? Is this clear? Like if you have Kmn, where, okay, except for K11, the diameter will be 2. Why the diameter is 2? Very simple, because between these two vertices, you have a path of length 2. Between any of these two vertices, you can definitely get a path of length 2. Okay, so that is the idea. This is the diameter. One more thing, tell me, ageless graph, can I say that is ageless graph, En? Is this complete bipartite? Is this complete bipartite? The ageless graph. Can I say this is complete bipartite? Like for example, this E4. Can I say this E4 is complete bipartite graph? Tell me. Yes, this is complete bipartite graph. You can put A, B, C, D, all of them here. You can put all of them here. Very simple. So yes, this is a complete bipartite graph. Is this a complete bipartite graph? Yes. Just put all the vertices here. Just put all the vertices here. Then remember, you cannot do like this. Tell me, can I do like this? Tell me, can I do like this? Please tell me. No, I cannot do, because now this is not a complete bipartite, but I can do this. Okay, so just keep this empty. A part can be empty. Okay, so there is no problem. So this En, this is complete bipartite graph. There is no problem. Okay. And so this is the idea. Okay, all the things we have seen. If anyone has any doubt, you can ask. This is enough for today. Please let me know if you have any doubt. Anyone, any doubt whatsoever? Is there any doubt? Hello, Arpan?
Yes, sir. So the degree sequence of K of Mn, the complete bipartite graph, I did not understand. Can you just repeat that?
So tell me, what is the degree sequence of K24? What is the degree sequence? Tell me the degree sequence of K. This on one side I am writing degree sequence, and you tell me the degree sequence of K24. Create K24 and tell me the degree sequence for K24. K24 means like this. You have two vertices here and you have four vertices here, and basically every vertex in one part is adjacent to every vertex in another part. So tell me what is the degree of this? Tell me what is the degree of this? What is the degree of vertex 1?
Vertex 1 will be 1 only.
Degree of vertex 1, that is 2, because 1 is adjacent to a comma b. Degree of 2 is 2, degree of 3 is 2, degree of 4 is 2, because
Yes.
these vertices are adjacent to both a comma b. This is complete bipartite graph, K24.
Yes.
What is your K24? K24 means you have two vertices here, you have four vertices here. This is your K24, and this is the idea of K24. In K24 means this is a complete bipartite graph. This is a complete. This should be bipartite, means two elements here, four elements here, and this should be complete. This should be complete. What that means? That means that all the possible edges must be there. All the possible edges must be there. Don't put edge here because it should be bipartite. It should be bipartite. It should be complete. So all the possible edges you should put. Okay, so I can say every vertex here is adjacent to every vertex here. So similarly, this B also will be adjacent to everyone. This B also will be adjacent to everyone. Now tell me what is the degree of these people? Degree of 4. What is the degree of 4? What is the degree of 1?
Yes.
Degree
2.
of 1 is 2.
Yes.
Degree of 2 is 2. Degree of 3 is 2. Degree of 4 is 2. And degree of A is what?
A will be 4 and B will also be 4.
Yes, degree of A will be 4. You can notice degree of A will be 4 and degree of B will be 4. So finally, what will the degree sequence? That will be 4, 4, 2, 2, 2, 2. Basically, 2 times 4, 4 times 2. 2 times 4, 4 times 2. For example, if you have 3, 7, then what will happen degrees to the degree sequence? There will be 3 times 7.
Yes.
There will be 3 times 7 and there will be 7 times 3.
Times 3.
Are you getting my point? Because
Yes.
see, because this will be the degree of every vertex in the first part. This will be the degree sequence of every vertex in the first part. So this will be for X and this will be for Y. Okay.
Exactly.
Any
Understood.
other doubt?
No, sir. Thank you very much, sir.
Any other doubt, anyone? Please let me know. Don't keep any doubt. We have seen many topics like bipartite graph, complete bipartite graph, all the topics. If you have any doubt, let me know. Hello, Manideep.
Uh, hi, sir. So I
Yes.
have a doubt that a graph is called k-regular bipartite graph if all vertices have degree k. Prove that it is a bipartite. I haven't understand it.
See, if you have a bipartite graph, then the total degree of two parts will be same, right?
Yeah.
Did
Correct.
this you understood?
Yeah, I understand.
Bipartite k regular. This is your question. This is your question. You have a graph which is bipartite k regular. Your graph is bipartite and k regular graph. This is your
Okay.
graph. Now, because it is bipartite, so the two parts will have total degree will be same. I can say total degree of this part X. I can say total degree of part X will be same as total degree of part Y.
Yes.
Correct. Why this is happening? Can you tell me why this is happening?
Whenever we add a vertex that will connect to y.
No,
we'll add
whenever we put some age, every age will increase the total degree of X will +1 and total degree of Y by +1. Every age, whatever age I put, the total degree of X will go +1, the total degree of Y will go +1. Whatever age I add, if I add this age, then total degree of X will go +1, total degree of Y will go +1. So, like it's like this, every age will give +1 to this and +1 to this. So the total degree of this will be equal to total degree of this. This is correct. This is clear.
yes.
Because remember, every age will give +1 to this guy and +1 to this guy. So these two people, they will have total degree will be always their same. Now, because this is k regular, because this is also k regular, this is bipartite, but this is also k regular. So every vertex has degree k, yes or no?
Yes.
How many vertices you have here? That is cardinality of x. How many vertices you have here? That is cardinality of y. So tell me, what is the total degree of this part x?
K into mod x.
Yes, because every vertex has degree k. This is k regular. So every vertex has degree k. Okay. So in this part x, these many vertices I have. So the total degree of part x will be k into cardinality of x, and total degree of part y, that will be k into cardinality of y. You can cancel k to k. So finally cardinality of x should be equal to cardinality of y. This should happen. Okay, so in every bipartite k regular graph, this should happen.
Okay.
Any other doubt?
1 second. That's it, sir. Thanks.
Anyone has any other doubt? Let me know. Anyone, any other doubt? Graph theory is very important. And in graph theory, we will study everything, all the variations, all the questions, all the theorems, all the concepts, everything we will study, and we will connect. Can you notice we are connecting all the concepts? Every concept that we have seen so far, many times we connect them. Many times we create a question. In that question, we use many different concepts we use in the same question. So in the graph theory, all the concepts are connected to each other. Every two concepts, they are connected to each other. And this is what we will do. Okay. Thank you, everyone. Thank you.